All right, so last class we started talking about the antiderivative and what I eventually ended up turning into calling it the integral. And we were looking at how the integral basically breaks up the area under the curve into boxes to be able to figure it out. And the last problem that I did was to actually show you what was known as a definite integral, to show you that the answer for the problem that we had done came out to be the exact same as what we got when we did the limit. So we're going to start looking at some of the properties of a definite integral, and we're going to going through the beginnings of basic integration tonight. And then next week we will look at probably the most complicated thing, which is the substitution rule. And that'll be the last new thing that I teach you for integration. So a couple little things first. There's some properties that are very important to look at, and how we use them actually is helpful. So the first one is when you're looking at an integral, that is the integral sign. And this is the interval we're looking at. So start to the end. If you reverse the beginning and the end, you get a negative. All right. So if you go the opposite direction, the answer is just going to be negative. So that's basically what this rule says. If you switch the start and the end, we end up becoming a negative version of it. And this one, if my start and end are the exact same point, it's 0. The second one should be pretty self-explanatory, but they are important to actually end up knowing. They do come up in some places. Another thing. And every one of these rules that we're looking at right now, also, even if there isn't an interval here, so these are definite integrals. Why isn't my pen working? Even if we were to get rid of the a and the b, the beginning and the end point, that becomes an indefinite integral. All these rules that we're looking at still apply. So there's nothing special about having the letters there that make these different. So the first one is that constant rule. Like, I can pull out the constant. If it's a constant just by itself, it's literally a box. So I can literally pull the constant out and just deal with the problem as it sits. Addition and subtraction, 2 and 3, we can split up addition and subtraction just like we did for the differentiation. And 3 is similar to what was 1, is if I can pull out a constant, I can pull it out of the whole thing. So pretty straightforward, simple ones. Okay, let's look at one and I'll break down all the different pieces in it. So here's my integral. this piece right here, that means the derivative of x, just like we had the dy over dx or the d dx, those type of things. It still stands for the derivative of x. The integral and the derivative will cancel each other out, so you do not need that part. You end up getting rid of that part at the end. What we use it typically when we're looking at integration is that tells you which the variable you are integrating by. So if it's an x, we're looking at the x's. If it's a y, we're looking at the y's. If it's an x and there's y's in the problem, we have to do something else with it. So that becomes a lot more important when we're looking at some of the higher stuff in Calc 2. So let's look at this as a simple integral. What is the integral of 4? We can split this up. So what is the integral of a constant?
0.
That's the derivative of a constant.
The constant itself.
Times x.
Times x.
So we're basically going backwards. So if you remember, if we had the derivative of 4x, that would just be 4 because the x would disappear. So integration just goes backwards. So this is 4x, and we're evaluating it from 0 to 1. So what that 0 to 1 means, it means I'm going to plug in 1 and 0. And I'm going to subtract the two values. So we plug in those values for all the x's. So this becomes 4. All right, what's the integral of 3x squared? Yes. Because we're going to divide by 3, and that ends up canceling out the other 3. So this just becomes x cubed. And again, we're evaluating it from 0 to 1. So I have 1 to the third minus 0 to the third, which is 1. So this final answer is 5. So if we were to look at this as a graph, this is, in essence, what it's actually defining. My x-axis to go from so that 4, if we're looking down here, that's where that 4 came from. is that box right down here. 1, 2, 3, 4. That extra 1 that we got is the area of this piece right here. Okay. So when we're looking at that definite integral, that piece right there, that's the 4. And this piece right there, that's the 1. Because all I did is I basically shifted it up, and that's the area that I'm going to count. That makes sense? Yes. That is one of the applications of it. It's a big application of it because we actually, when you expand it out, we actually can use it to find volume. We can use it to find surface area. We can use it to find vectors and things like that later on down the line. But one of the big things is looking for that area because it's looking for that cumulative change is in essence what it's looking for. So we had the derivatives, which is looking at rate of change, but the integration is looking at the sum of everything underneath it, which is in essence the area under that curve. And we can look at it in terms of the y going towards the y-axis and everything else too. So this is just the beginning of it all. The hard part about integration is going backwards is always harder than going forwards. So there's going to be certain things that were really easy in the derivatives go one direction, but to try to undo that becomes a lot more complicated. Just one. This one. All right. Find me the beginning piece of this one. All right, what do we got? You can ignore this until you've done the integration. So what's the integral of 4x squared? 4/3 x cubed. Integral of x. Not you. Yep, or x squared over 2. And integral of 2? Somebody else. Thank you. And then we're going to evaluate it from -1 to 2. So we have 4/3 x times 2 to the third plus 1/2 2 squared plus 2 times 2 minus 4/3 times -1 to the third plus 1/2 -1 squared plus 2 times -1. 32/3 plus 2 plus 4 -4/3 minus 1/2 plus 1/2 minus 2. There is a reason I left them in the parentheses. It is really, really, really easy to screw this up and forget to distribute the negative sign through to them all. You'll get the first one, you'll probably forget the other two. So it's a good habit to get into until you get really good at being able to catch them, put them in parentheses so you don't make that mistake. So this becomes plus 4/3 minus 1/2 plus 2. So I get 36/3, which is 12. Plus minus 1/2 plus 8. So 20, so 39 halves. Finally. All right. This is the fundamental theorem of calculus. Well, the first one. all this says, and this is why some people absolutely hate all those words. Say if you take the derivative of an integral, it cancels themselves out. That's all it says. That rule right there basically allows us to take the integral, a derivative of an integral, and they cancel each other out. They become back to the original function. So if I wanted to find the derivative of this, since it's the derivative of the integral, they cancel each other out. And we're evaluating from 0 to x. So we're not technically evaluating it. We're just going to plug it in. So then the derivative of that function is 1 plus x squared. That's it. The only reason I'm showing you this one is because this one shows up in Alex, and I'm not sure if I removed this topic. There is one catch to these. Notice how this right here is an x. If it is not an x, something else. So if that is anything but just a simple x, you have to do the chain rule on that. So this one ends up becoming secant x to the fourth times, what's the derivative of x to the fourth?
One-fifth x to the 5.
That's the integral. This is the other thing you're going to have trouble with in a little bit. You're going to get really quick to be able to switch. You have to switch back and forth between them. It's really easy to make those mistakes. 4x to the third. So that is my final answer for that. This one we've actually already done. The fundamental theorem of calculus part 2. Just says that we can plug those pieces in and actually find the answer. This is literally what we did at the beginning of class. When you were plugging the numbers in, that's all that rule says. All right. Find my integral. What is the integral of e to the x? E to the x. And then we're going to evaluate it from 1 to 3. So this becomes e to the third minus e. Okay. There's nothing you can do there. What if I did 0 to the third? So it'd be e to the x from 0 to 3. Right. Because anything to 0 power is 1. It's really easy to get into the habit of seeing when you have 1, you don't have to worry about the second thing. There is situations where that 1 matters. Or that 0 matters. So don't just get into the thing, oh, I only have to do one side when I have the 0. When you're doing the polynomials and stuff, yeah, it's going to cancel it all out. But it doesn't always take care of everything. All right, what's the crazy thing about this one? Huh? Yeah, so this actually right here is no different than if I wrote it like this. You'll see sometimes if it's just a 1 up top, they will put that dx up on top. Because in essence, you're just multiplying those anyway. So it's like you could easily move it back down. So what is the integral of 1 over x?
The natural log.
Yeah, this is the natural log. Remember, it's x to the -1. If I added 1, I get 0. That wouldn't work. So this is the natural log. So it's ln of x from 3 to 6. So it's ln of 6 minus ln of 3. Can I change that? Can I change it or no? Greatest of it, but it works. Remember your rules for logarithms. So this becomes, which is just ln of 2. Would I mark this wrong up here? No. I take off a point or two. But the thing about a lot of these is, as you start to do more and more with it, the simpler you can make your answer, the better it's going to be for you. And while this one had numbers, so it came out to be a simple thing, if this was just with variables afterwards and we were doing a bunch of things, it might be easier to put them all together to get a single answer instead of having the multiple pieces. All right, how do we set this one up?
The x.
So-
bottom is 0 and the top is b.
Yeah.
So 0 to b.
So that's the beginning setup of it. Even though it's not a number, it's still an interval. And then to be cosine of x dx. Why do you think that part's important. If we're not really using the b anyway, why is that important? It does give me an endpoint.
This cosine is a way so
It does repeat. What happens after pi over 2 for cosine? It crosses 0 and goes negative. So the bottom part, then my area is going to start canceling each other out. So in that respect, I might have to deal with something different when I'm plugging things in. So that's why the b, keeping it to the positive section, doesn't have that impact. We'll see how that actually impacts things in a little bit. So it's the integral of cosine of x. That's the derivative. It's sine. Remember, sine, cosine, negative sine, negative cosine. That weighs derivative. That weighs the integral. So then we're doing this from 0 to b. So it's sine of b minus sine of 0, which ends up being just sine of b. All right, find me the mistake.
Integral of 1 over x squared is 1 over x.
Yeah, but that's actually what they have there, really. Because the x to the negative first. It's really just negative 1 over x. That's not the mistake. I plug in negative 1 to the problem. I get negative 1 over negative 1, which is positive 1, right? But then I'm subtracting it. So if I plug in the 3, I get -1/3 minus, if I plug in the -1, I get -1/-1. All right, one more guess.
-4 everything outside of that. The -1 to 3.
No, but you're kind of hitting on something that's kind of important. But that's, yeah, the answer doesn't have anything to do with the original interval. That's the graph of 1/x². If we're looking at this from -1 to 3, that's the area. What do you notice about this?
Positive.
Okay. Yep. What else?
The asymptote. The vertical asymptote.
I have a vertical asymptote in this one. That goes to infinity. Okay. So the error in this problem wasn't in its calculation. The error is in the original setup of the problem. I can't go from -1 to 3 because 0 is not in the domain. Your integral can't find the value of a function that is using something that's not in its domain of the function. So in this case, the 0 is not in the domain. So when we look back at my wonderful fundamental theorems of calculus, this statement right here, it has to be continuous and differentiable on that interval. If it's not, I can't do it. And that one was not continuous on that interval. It's also not differentiable. So you just have to keep that in mind when you're doing them. Less useful for the problems because we're going to give you the problems and they're probably going to work, but more when you actually do it on your own.
So every time you have to check if there's an asymptote.
You want to check and make sure your domain that works for your domain. Yeah, you don't necessarily have to check that it's there's an asymptote or anything else. You just want to make sure that it actually works at the values you're looking for in the domain of the function. All right, here's all your integrals. Well, all the ones you know, so you're going to know so far. Pretty much all these are the antiderivatives that we looked at last time. So, oh, we didn't change the screen back. Sorry. There you go. Pretty much all these are the antiderivatives we looked at last time. They're just written in the opposite direction. So the only difference between what we were doing before, what we're doing now, is there are no A and B. So write the function down and I'll switch back over. And then I'll switch back so you have the integrals.
What's the A and B for the interval?
There isn't any. This is an indefinite integral.
Just like the whole.
Yeah. The only difference is your last step, you don't have to plug the values in. But you do have to put a plus C after it.
So indefinite interval is the integer or find the integer.
The what?
Find the integer.
Yeah. All right. What's the integral of 10x to the fourth?
Two x to the 5.
Sorry. What's the integral of secant squared x? Secant squared x is tan x. Plus C. So whenever you do your indefinite integrals, you have to put the plus C. Because in essence, it's all these values. I don't know where that graph fell on. We could have shifted it up, down, left, right. Well, up and down, not left and right. So that plus C is important. All right, try this one. Write it down and I'll switch back over to the other screen so you can have the table. There you go. I swear you can do it. I'm not lying. Those are really the only ones you know. So how are we going to solve this one? Remember back, so how many of you took pre-calc last semester? Okay. Remember that section in the trig where they told you, they gave you a problem and they said it equals this, and you have to go through all the steps to try to prove that it equaled that? Yeah, this is why. We have cosine over sine squared x, or cosine x or theta over sine squared theta, but we don't have that. We have to pick one of the things on the other side to match it to. So the sine's probably not going to help me. Cosine's probably not going to help me. I might be able to get secant squared x, but it's going to be, so like if I could do that, I could have secant squared x. Oh, sorry, that's cosecant squared x. Cosecant squared x, cosine x. But now I have multiplication, and we still don't have rules for multiplication. So that's probably not going to work. Because it's not going to come out to be one of the two nice multiplication ones I have here. So can I get it to be one of these two? Huh.
Separate the cosine over sine and multiply it by 1 over sine. Multiply them together. And if you rewrite cosine theta, sine theta as the cosine theta, and 1 over sine theta as cosine theta.
I swapped them just to match up with that. So then my answer is negative cosecant theta plus c. Knowing how to manipulate your trig functions is going to serve you very well. Again, when you're looking at these, even when you have all the rules that you're going to learn in chapter 7 and calc 2 for figuring out how to actually do derivatives of multiplication or integrals when you have multiplication, integrals when you have quotients, you never want to do those rules unless you have to, because they are a lot harder than doing it other ways. So while this is a quotient, you would not want to use partial fractions to split this one up and do it, because it's a pain in the butt to do. You want to see if you can use algebra to simplify the problem first. So this one, I can easily break up and simplify it. I literally can just split that under each of the pieces individually. So the first one's 2 plus, I'm just going to change that to t to the 1/2 minus t to the negative second. And now I can do the problem. So I don't have to go through and do this massive problem out. I can do it, simplify it down before you do it. You always want to do that first. So now I have 2t plus t to the 3/2 over 3/2 minus t to the negative first over -1. So 2t plus 2/3 t to the 3/2 plus 1 over t. Evaluated from 1 to 9.
Shouldn't the integral 2t be t squared?
Did I screw that one up? It wasn't 2t. It was 2.
Oh, you're right.
I was like, look, because that's an easy mistake to make. So that's look. 18. 3, 27, 9, 18. Minus 2 minus 2/3 minus 1. 36. So 33 minus 6/9. I typically wouldn't leave it as a mixed number, but I really don't want to have to multiply 32 by 9 4 right now, or 9 right now. All right. All right, find me that one. All right, what's the integral of cosine of x? What's the integral of cosine of x? Sine x. I have sine of pi minus sine of 0, which is what? Does that make sense?
Yeah.
So let's look at cosine of x. So here's cosine of x. This part and this part are exactly the same. So I have a positive area here, and I have a negative area here, and I'm going to cancel each other out. So I have 0 area. Now, that wouldn't be very useful. So nothing you did in this problem is wrong. That's right. However, it's not very useful to do it. Sometimes when you're looking at this, what we want to do is we actually want to do the absolute value of cosine of x. That way you're going to get the area of both of them split. However, the way this is written, I need to actually split this up. So because I'm looking for the absolute value of cosine of x, I want to actually split it up into the two pieces. So I'm looking at it as two separate parts. So I'm going to find the integral from 0 to pi over 2 of cosine of x. And the integral from pi over 2 to pi of negative cosine of x. So that would be sine of x from 0 to pi over 2. And this would be negative sine of x from pi over 2 to pi. So I have sine of pi over 2 minus sine of 0. So I have 1 minus 0 is 1. Then I have negative sine of pi over 2 minus negative sine of pi. Oh, I have it backwards. I'm like, wait a second. I know something was wrong. That's why. There we go. There we go. And we add them together. Now that area makes a little more sense. That really comes into play when we're looking at a problem like this. So particle moves along a line, so that its velocity at time t is that. I want to find the displacement of the particle during the time period 1 to 4. So what's displacement mean?
Uh, shortest distance between the starting point and the end point.
Yeah, how far it moved, like the actual distance from where it started to where it ended. Not how far it actually moved, because it could move in a whole bunch of different places, but the actual distance between where it started and where it ended. So I have my velocity. How am I going to be able to calculate distance? What do I need to find for distance?
The integral.
Because of why? Why do I need to find my integral?
Um, the area under the curve gives you like the total.
Nope. I have the velocity. What's the integral going to give me? Position. So if I know the position at the beginning and the position at the end, I can calculate distance. So in this one, yes, integrals technically still calculate area under the curve, but that's not what I'm looking for in this case. By finding the position of it from the velocity, I actually will find the distance. So the integral from 1 to 4 of t squared minus t minus 6 dt. So how did it move? So what's the negative 9 over 2 represent? Okay, so it's moving to the left. That's actually very, very important. So it's left 4.5 meters. All right. The second part of this question says find the distance traveled. So how am I going to find the distance traveled? And is the distance traveled different than the displacement? So the question really comes down to being, did the particle change directions while it was traveling between 1 and 4 seconds? So how can we figure that out? How can we tell which direction the particle is traveling?
The velocity,
Okay. What about the velocity?
whether the velocity is positive or negative.
All right. So if the velocity is positive, it's moving to the right. If it's negative, it's moving to the left, right? Okay. So we know the velocity. We just have to figure out where it's positive and where it's negative. Okay. So to figure out the velocity and figure out where it's positive and negative, what do I need to find?
From zeros.
Right, the critical numbers. So in this case, it's the 2 zeros. So factor it for me. With 2 numbers multiply -6 and add the -1.
Create a positive two.
So t equals 3 and t equals -2, where it changes direction. Do I care about the -2? Right, we're only looking at that area anyway. So number line with a 3 in the middle, 1 there, 4 there. So pick a number. Pick a number. Uh, 7/2. So 2 is going to be negative and positive. So this is going to be negative. 7/2, it's going to be positive. That's going to be positive. So that's positive. So when we're looking at my integral, I'm doing the integral from 1 to 3, and it's negative. So I want the negative version of that. So I'm going to do negative t squared minus t minus x plus the integral from 3 to 4, and that one's positive, so I don't need to change anything. Now, what was the very first rule I talked about tonight? Was the very first rule that was on the screen. Oh, come on. I know you're not going to necessarily remember next week, but you got to remember an hour ago.
The integral A to B, or the integral from B to A is the integral negative A to B.
Right. If it's a negative sign, I can just swap the two things, right? So I could actually take this problem right here. Actually, I could take this and just change it to the integral from 3 to 1 of t squared minus 2 minus 6. Now, why would I want to do that? Because I already have the integral of t squared minus 2 minus 6. This saves me a step. I don't have to redo it. I already know what that answer is. I already have that problem. I have it back here. So I just have to do this from 3 to 1 plus from 3 to 4. The top number is always your first one. So I have 1/3 minus 1/2 minus 6 minus 3/3 is 9 minus 9/2 minus 18. Yes, because I don't feel like doing it all out. Approximately 10.17 meters. So over the course of that path from 1 to 4, it traveled approximately 10.17 meters, but only actually changed position by 4.5 meters. So while, yes, the integral can help us find the area under a curve, it's not the only thing it can do. It still does the concept of the antiderivative piece where we can look for positions and everything else. Yes, we have class next Tuesday. So I will see you next Tuesday. And I will have your tests. I will probably have them graded on Sunday. That's my plan, to have them finished by Sunday. So I'll do this stuff up there on Blackboard. Probably before you take your test back. Tomorrow, I totally forgot to put it up there. I'll put them both up tomorrow morning. Welcome.